Here are my co-authors. Sarah's going to come run up and do 2 slides. Oh, there you are, because she's the one who worked on them. We're going back to the beginning of this whole thing, which is the ecological departure metric. It used to be called fire regime condition, class fire regime condition. So we're revisiting the beginning. And this beginning has not changed for decades, practically not. And we think it needs to. So ecological departure, which is called vegetation departure, I think, in land fire, is non-spatial, symmetric, and it's not stochastic. There's no replication. There's software replicate, random number generated stuff, but that's not what we're talking about here. The objectives here is to develop a spatially explicit ecological departure metric. ED is the term here I'm going to use, with a moving window. And spatial is not the same as spatially explicit. And we also want the window of assessment to think of distant pixels that are far, far away having little to no contribution to what's happening locally. So and we're introducing that, and we want to create a stochastic version. We've always been frustrating. There's only very few people who've done that. Corey Blankenship and Company is one of the few that's done it. So 101 ED. Ecological departure is the same as in the vegetation departure in the new land fire. It used to be fire regime condition. The class part is the discrete version of that. And it's a simple metric of dissimilarity. It's 100 minus the sum of all the minimum of the expected and the observed value, observed remote sensing and all that. And expect is your reference condition. Give you a simple example. This is a Mount Sagebrush description of vegetation classes, early successional to late successional, and we put in a hodgepodge here, all the uncharacteristic class. In my models, there's like 30 of these, but this is a very old slide that I recycled. And basically, you have a first column is what you obtain from remote sensing. So this is the percent of this early successional class in your landscape for Mount Sagebrush. And this is the reference condition for the historic range of variation. It's the same terms. And in this, you have too little. You're supposed to have 20% and 50% of these 2 classes, and you only have 1 and 6% according to your remote sensing. So you have too little of those classes, and you have too much of the stuff that's in green, especially this. So as a manager, you want to move the green stuff to the red stuff. That's your job as a manager, to do that, and you have a limited budget. And the dissimilarity is the difference between these 2 columns of number. That is ecological departure. There's no, in this formula, there's no measure of variance. It's just one measure that's not spatial. So imagine this is one of our landscapes that we did assessment for Barrick Gold Corporation. And you have the 2 arrows there pointing at black sagebrush. And this is an administratively defined landscape. It's just, there's no ecology for this landscape. It's just administratively defined. And pointing at the 2 arrows, those 2 arrows will have in the traditional ecological departure the same exact value. 60% departed, but there's actually no rhyme and reason to 2's area. Not only that, but the 2 subpopulations of sage grouse here are unrelated. They're distinct. So what's over there and here has no bearing on one another, yet there is one value. And that bothered the living hell out of us. Also, the TNC species managers think of, the land management agency thinks of threatened endangered species management mostly. That guides a lot, fuel management, invasive species management. And so they kind of have a mindset or consideration of things that are more local. So stuff that is like literally 50, we work in landscape where those 2 points are about 30 kilometers apart. What happens over there is of no consequence what happens here. And this bothered us. And also, as you can imagine, right here where you have fuel breaks in the mountains and all that, in that open area there, the reference condition could be very different locally. You can have a lot of late successional classes. Here you actually have trees around the pinyon juniper, and the reference condition there, the percentage of the class could be very different and be a totally valid but different reference condition, somewhat similar, but different. And now Sarah is going to explain the spatially explicit part.
So these are the different realizations of the maps after a couple hundred years. So essentially the reference condition. And what I'm doing is I'm comparing the current condition to all these realizations of the condition. And to do that, I'm going cell by cell. I developed this in R, working on Python because, and this is a big data set. So it's a moving window going cell by cell. We applied this distance decay function within it, and we just used a really simple, what you call it, exponential decay. So something far away has an impact compared to something close. And within that window, it's a pretty easy. You're just taking a proportion of all the different classes of, let's say, a black sagebrush, and you're just counting. And from there, you get that percent breakdown that Louis showed before, where it's 6% A, 20% B, etc. Yeah. So with each cell, you get that.
Okay, great. She'll be back for another slide. So the radius of the window is user defined on depending on your management objectives. Sage grouse, 10 kilometers. Pygmy rabbit, 500 meters. And this could be a flat line, so all pixels contribute equally. This is user defined too. You could put a straight line if you want, but you have to have a management question to define both the radius and the shape of the function. Oh yeah, and for class A, the weights, these weights divided by the weights among all class is your observed proportion. As simple as that. The reference condition, the stochastic reference condition is the other part of this. This is a tumbling JR landscape. It's in central Nevada. We had done the remote sensing for this in 2014, and then we never had an opportunity to use this for management. Barrick Gold finally sold their interest in the ranch there. So what we did, we took the current vegetation class obtained from remote sensing, and we interpreted all the uncharacteristic vegetation class back to what we thought was the most likely pre-settlement type of vegetation there. The ones that were already in reference condition, we didn't change them, obviously. We did 20 replicates. These are spatial replicates. We're not talking about temporal replicates. And we ran this for 700 years. And the simulation, the first time we did it, ran for, the first one I did before I optimized some stuff, ran for a week and a half on a server. So they run for quite a while. We optimized that since. So now, stop the simulation at year 700. You have 20 rasters of vegetation. And those 20 rasters, the proportion provides your estimates. That's where you estimate the variance from. It's not more complicated than that. We did not use temporal variability within the replicate because it's potentially autocorrelated values. And we stop the simulations pretty much when it reaches equilibrium. So we know the values before were not at equilibrium. So why would you use that for replication? We don't. So we do not use temporal variability within replicates. It's always among replicates. So it's a true estimate of variance. Here's an example. We have 4 out of 20 SyncroSim simulated rasters. You'll notice the colors are very, very different among them. And what you have to remember, these are a small portion of a landscape, and these rasters will persist for decades. This vegetation is slow growing. So this raster, this reference condition is perfectly as valid. Not only that, but will persist for 30 years. So this is, there's not one reference condition. That's what we're telling you. And therefore, we take these, the whole landscape, the whole 400,000 acres, and then Sarah runs her moving window thingy with this thing and does a calculation. It's the reference here for the pixel there for which it's not the reference here. So everything is to that pixel. It's all defined at the pixel level, the reference condition and all that. Matching moving windows. It's total synchronized geographically. So you use the same exact formula we have, and therefore once you've done this, you have all the numbers to get results. So this is the landscape. This is the traditional ecological departure, and everything's gone to hell because of cheatgrass. So you have a little bit of the blue stuff that's in better condition. These are wet system. Intermediate values at higher elevation. And if you do the spatially explicit one, then you'll notice things are switching. So this value here that's better is the same ecological system, but this one actually got worse. They're both mountain sagebrush. This got better. So it allows you to actually define the areas that that are very different. And also shows you that this stuff you thought was in good shape is actually not so good. And so, and the variance on this is the raster, the variance is obviously the intermediate values where you have the highest variance values, because everything is bad or everything is good. There's not any variability. It's the midpoint. So that's not very impressive. What's impressive is that there's actually low variance. I was showing you the 4 replicates and they look quite different. But despite that, the variance is actually quite low. So there's very stable result. But we did more. And if you phone in the next 10 minutes, you'll get an extra one free. Landfire did the multiple system ecological, the fire regime condition. No one ever used it. No one had a use for it, so it's never been used. We use it. We developed our own algorithm and we made it a multi-system. So, and the reason for this is, imagine you're a mule deer and you're sitting on your little carpet pixel right here. What you do is that you consider the whole habitat because you browse from everything. You want the water, you want the riparian system, you want the thermal cover for the winter, you want the different amount of browse. So for animal perception and natural perception, you consider the whole thing, the whole system. Even sage grouse that are sagebrush obligates need wet meadows and they use mountain shrubs. So they use at least 3 systems. So they have a perception that's more natural. And when our real estate folks at the Nature Conservancy go out in the field, they're not just looking, oh, well, black sagebrush is just like this. No, they look at the whole enchilada. So this is a more natural view of the world. And the formula is that you take the proportion of class as we calculated before with the weights, and you just prorate it to the proportion of the class of the system in that little window rate with the radius and all that. And what happens is that big systems that dominate the landscape are suddenly not dominating the influence of the small systems. So in your window, that little wet meadow that is critical for many species suddenly rescues in maybe in good shape actually is counted as if it were equal to the big systems. But the big system is bad way, way over there where it has no consequence to that assessment right there. So the systems in better shape actually rescue things and increase and decrease the ecological departure. So something I didn't mention. The lower the ecological departure, the better. It's like a score. So this is why it's generally better. The lower the score, the better. But basically, the landscape always looks better with that, and the variance is low in general. The bag of tricks. There's little tricks here. We represent the vegetation by an 8-digit code, 5 digits for the system, 3 digits for the class. Each pixel has a unique 8-digit code. No, and Sarah explained to me, at any one time, you're only dealing with 120 codes as opposed to 500. We have like 500 of these codes in the total landscape that are possible. So she creates a lookup table of only, and the smaller the digit, the faster the code and the less memory required. That makes enormous difference in computation. Don't use if then else statements. There's little tricks she does that decreases the code by an order of magnitude, the time, the duration. So it's pretty amazing. Technical development. This is ED. We want to generalize it to the unified ecological that we use in STSIM or SyncroSim. There's a package called reference condition or reference departure or something like that. It's the measure of unified ecological. We paid Apex to do that years ago. I want to revisit that equation to make it more elegant. The one that's there is clunky. And so we're working on this actually right now. Also, Anna asked me, what happens if you're in Australia and we have like 50 species, each with their own home range? How do you pick a home range for your moving window? And I didn't come up, she did. The species area curve, Preston, 1952, the famous Charles Preston, proposed a species area curve. It's one of the most strongest relationship in ecology. You can say the area of my sampling plot that corresponds to 90% of the species captured, especially all your TNE species you may be tracking, that could be the size of your moving window. If you only have data on broad taxonomic groups like lizards, mammals, or plants, then you'd perform the species area curve in there. So I capture 70, 80% of my species in a plot of 10 acres or 10 hectares. Actually, in Australia, it would be 10 hectares. And that's your moving window. Or you take the maximum home range among your TNE species. We're always single species. And Jim was asking me, we did. This was a presentation I gave here in 2018. And it's what clustered system. And this is the real reason we developed the spatially explicit ecological departure, is to address conservation at very large landscape with clustered system. When you cluster system, like you blend together black, those sagebrush and dwarf sagebrush, the reference condition means nothing. It is invalid, actually, unless it is spatially explicit, because it varies along gradients in system. That's why, Jim, this was the real result why we actually created this at the beginning, is to answer geographic scale assessment with cluster. You have to simplify when you get these. You always simplify when you get bigger and bigger. Otherwise, you'll just lose it. Okay.